Good day. My name is Stanley Esaduwha from Physics Department, FC Yola in Nigeria. I'll be presenting a paper titled Speed Sensor Study Using a Single Fiber Bragg Grating, FBG. Now, fiber Bragg gratings have changed the way we do sensing and communication. They're actually one of the best inventions of the last decade due to their ability to be deployed in very harsh environments for the prediction of natural disasters such as earthquakes. Now, these sensors have been employed for years in very harsh environments as alternative to electrical and mechanical sensors that are very susceptible to electromagnetic interference. But one advantage of FVGs is that they are very accurate. They have longer stability. They are smaller in size, and they are very immune to electromagnetic interference. And they have been employed in sensing systems for measuring physical quantities such as temperature, strain, and what pressure. And the references are actually attached. And FBG is actually a short length optical fiber that actually filters a particular wavelength. It's a periodic perturbation of the refractive index along the fiber length, which is formed by the exposure of the core to create an intense optical interference pattern. Now, when these perturbations are these perturbations are affected by UV radiation interference exposed to the core of this fiber. So for this particular study, the FBG is used as a strain sensing purpose due to what bending. When the FBG is strained by wind speed, there is a shift in the Bragg wavelength due to the strain produced. Now, this study actually investigated the effect of wind speed on the transmission characteristics of FBG with particular emphasis on the Bragg wavelength shift. Now, what you have is a schematic diagram of our experimental setup. Now, what you see here is the wind tunnel, and with the FBG in between. So the FBG is if you see the FBG is very straight, it's not strained in any way. So we have our OSA, our anemometer to measure the wind speed, and all right, when the fan is turned on, the speed of the wind impinging the FBG was varied, by controlling the number of revolutions the fan makes in 1 minute. Now, the impact of the wind on the FBG actually made it to become bent. Now, the wind speed and the wind pressure of the FBG was subjected to a monitor using an anemometer, and the values were duly recorded. From the experiments done, the wind speed varied from 7.22 meters per second to about 27.25 meters per second, while the wind pressure in the tunnel was from 39.90 to 450.80 pascals. All right, now this is set up to this is after the wind was introduced into the tunnel, and you can see the FBG now became bent. It has lost its straight structure, so it's bent now, meaning that it's undergoing some form of strain. All right, now the results and discussion. The Bragg wavelength and the wavelength shift delta lambda b were obtained using an optical spectrum analyzer after the Bragg gratings was strained by bending in the wind tunnel due to the action of a uniform flow of wind. Now, it's also evident from the transmission display on the OSA that the values of the Bragg wavelength and hence the Bragg wavelength shift are gradually increased by increasing the wind speed and pressure in the tunnel. So what that means is that there exists a direct relationship. So as you increase the wind speed, there's also an increase in the values of the Bragg wavelength and the shift. Now, the initial spectral shape was not modified as the speed increased because of a laminar flow within the tunnel. Now, what we have here is a table due to the variation of wind speed when the FBG with a central wavelength of 1280.334 nanometer is placed within the tunnel. So you see the table, wind speed from 7.22 to about 27.25. So what we have here is just the wind speed values and the wavelength shift and the wavelength. Now, as you can see, a linear relationship exists between the Bragg wavelength and the wind speed. That gave us a sensitivity of 0.0058 nanometer per meters per second. From the data recorded from the wind tunnel experiment, the plot of Bragg wavelength shift against which we gave a linear response and the sensitivity of that, as shown in figure 3 in the previous slide. Now, figure 3 shows the result obtained under variable speed conditions from 7.22 to 27.25 as a function of the Bragg wavelength shift from 0 to 0.112 nanometer. Alright, so you can see it's under table 2 showing us the relationship between the wind speed and wind pressure, because each time we had a wind in the tunnel, we also took note of the pressure as well. So the matching pressure was placed side by side with the speed at a particular time. Alright, so also a linear relationship exists between the wind speed and the wind pressure. So you can see from the diagram, we give us a sensitivity of 0.0463 meters per second per Pascal. Alright, so to further analyze FBG, the wind speed was plotted against the wind pressure data, and figure 4 shows a plot of wind speed against wind pressure in the tunnel. But we've discovered a linear pressure exists between them. Now, to test, so we wanted to see if my results are consistent. So I decided to use a second FBG that has a central wavelength of 1288.376. So we placed that onto the tunnel and subjected it to the first conditions as the first. So now this is the table that was obtained after subjecting it to after putting the new FBG into the wind tunnel. So this is what we have. So we had a speed that is running from 7.20 to about 27.30, and with the various wavelengths and their wavelengths and a shift in wavelength. Okay. So as before, we also have a linear relationship between the Bragg wavelength and the wind speed. So I would give us a sensitivity of 0.0057 nanometer per meters per second squared. Alright. So this is also a table for different wavelengths. So we also analyzed it comparing the wind speed and the wind pressure together. The graph was plotted, wind speed versus pressure. We also had a linear relationship between the wind speed and the wind pressure with a sensitivity of 0.0462 meters per second per pascals. Alright, so like we said before, linear response was obtained between these two for this particular FBG placed in the tunnel. Alright, now for the discussions, now we've checked the effect of wind speed on the FBG, and the Bragg wavelength shift with displacement and wind speed are clearly observed. Now this is due to what? The perturbations of the gratings resulting in transmission spectra. So we worked with two FBGs. Now we started with an FBG with a central wavelength of 1280.336 nanometer. So figures 3 and 4 showed linear responses when Bragg wavelength was plotted against wind speed, and when wind speed also was plotted against what? Pressure. So we had those values there: 0.0058 nanometer per meters per second and 0.00463 meters per second per pascals were the sensitivities that we obtained. Also, the FBG with a central wavelength of 1288.376 nanometer, as shown in figures 5 and 6, also gave us linear responses when the Bragg wavelength shift was plotted against wind speed and when the wind speed was plotted against pressure. So the measured sensitivities were also 0.057 nanometer per meters per second and 0.046 meters per second per pascal. So with this result now, at least a consistency between the first and second FBG was established. So and again, the sensitivities obtained from these experiments can be used to determine the performance of FBG when used in wind speed sensing systems. So in concluding my presentation rather, linear response we obtained a linear response with the wind tunnel experiment. Both FBGs used in the tunnel at different times were subjected to the same conditions, gave similar results. Even despite a difference in their center wavelengths. So because of the sensitivity of the FBGs, can be adapted to measure wind speed and wind pressure. So also these are the references that we consulted. I mean, what I consulted for the work, and thank you very much. And I hope we'll be able to do this next time. Thank you. Have a great day.